Hello everyone, my name is Ricardo Castaneda and today we're going to be talking about quantum computers. Hi, once again, thank you for watching this video of quantum computers. To begin talking about quantum computers, first I would like to talk about a law very important for computer science, to understand better the development of computers. Moore's law was created by Gordon Moore, co-founder of Intel. This law states that the number of transistors on integrated circuits doubles every 2 years. At the beginning, Moore predicted this trend will continue for at least 10 years. The trend has continued for more than half of a century. Current transistors are 5,000 times smaller than the thin of a human hair. With Moore's law, we can predict what the size of a transistor will be through the years. By 2020, the size of a transistor will get to the size of an atom, the smallest component of nature. Almost impossible to do a transistor smaller than that. As we get smaller and smaller, we cross the classical age to the quantum age. This represents a challenge because in conventional world, we know how things will react. As we enter to the quantum world, electrons behave like waves, and they no longer go into the computers like we want them to go. For that reason, a lot of people have speculated this will herald the end of Moore's law, but many scientists see this as the start of something new, where quantum physics and quantum mechanics will play an important role. Some people may see these predictions of quantum computers insane, wondering if computers aren't already fast enough. We have a lot of great technology, amazing computers at the reach of consumers that can do amazing things for us. Develop technology that allows us to have different electronic devices that run our lives much more easier. But there are complex problems that computers are not yet ready to solve, and do not have the capabilities of doing it or will take years to solve. These problems can be solved efficiently using conventional computers. An example of that is the salesman problem, which consists of a salesman who has to visit different cities and is looking for the shortest route. This can be a problem that grows in complexity and time consumption exponentially by adding more different cities to the problem. But please allow me to show you this video so you can understand this better.
And one of those is something called the traveling salesman problem. So here we have a salesman. We want him to travel to lots of different cities, and we want to work out where the shortest possible route is. That sounds like an easy problem, but it's actually one of those intractable, exponentially hard problems. So here we have on the screen the number of possible routes that he can take as a function of the number of cities. It's something that grows very, very quickly. So by the time you have 14 different cities, there are now already 10 to the power of 11 possible routes that he can take. So if I take a classical computer, it works in the gigahertz regimes, 10 to the 9 operations per second. And it can work out the shortest possible route in about 100 seconds. Well, that's no big deal. But now what happens when I go to 22 cities? There are now 10 to the 19 possible routes that that salesman can take. And with that same classical computer, it would take 1,600 years. Now, this is amazing. And if you look, by 28 cities, it's longer than the lifetime of the universe to work out what the shortest possible route is. Now I heard this problem many years ago and I just couldn't quite believe it.
After observing the video, we learned how today's conventional computer architecture approach these type of problems. A conventional computer follows logical reasoning by attempting each route and keeping record of time and distance for later on compare and make a decision in this particular example. This is because conventional computers check many different possibilities in rapid succession. On the other hand, quantum computers check many different possibilities in parallel, a very important concept that we will discuss more about it later on this presentation. For the moment, let's understand how conventional computers work. Conventional computers are built from silicon chips that contains millions or billions of mini-chip transistors. Each one of these transistors can be either turned on or off to represent either 1 or 0. This is how conventional computers process and store data using binary digits or bits. Quantum computers work under the same concepts but with different rules and capabilities. Quantum computers work with qubits represented in hardware using quantum mechanical states. Quantum computers may use the spin direction of a single atom to represent each qubit or the spin direction of a single electron, of a polarization orientation of a photon. Individual qubits can represent a value of 1, 0, or both simultaneously. Because the particles of a field used to represent qubits can exist on more than one state, they represent a superposition at exactly the same point and time. By touching a probability to each of these states, the single qubit can therefore use a wide range of values. As we can see in this picture, different examples of classical outcome states have to be usually either one or the other. With a qubit, a new superposition is achieved where the qubit can represent both outcomes at the same time. We learned how quantum computers work, with its unit being able to achieve a superposition. But why are quantum computers so much faster than conventional computers? The answer lies on the same grounds: superposition. Conventional computers take bits as 0 or 1s and then process an algorithm. With quantum computers, use qubit superposition, sort of parallel 1 and 0 at the same time. So what this means is that if we have a qubit, we have a total of 2 different states we can represent at the same time. If we have 2 qubits, that means that we have a total of 4 different states that we can represent at the same time. If we have 3 qubits, we can have 8 different states at the same time. This means that every qubit doubles computational power, and considering this, a 30-qubit computer will be much more powerful than a supercomputer. Thanks to this, the computer itself will exist in many superposition states of possible processes going on inside. That parallelism provides this exponential speedup of particular problems. After what we have learned about quantum computers, the idea seems great. We might be wondering how come we don't have already such quantum computers if we already know all of this. The answer is stability. Because quantum computers use quantum mechanics for their computations, they are extremely sensitive to any sort of external noise. An interference of any kind will upset vibration on atoms, creating nonsense. Actually, current attempts of quantum computers have to be isolated to avoid any vibration to disturb the atoms. Programming plays also an important role on why we are not seeing quantum computers' effects. Programming will be a challenge for programmers too. The whole future of computer aims towards parallelism. An important computer programming concept revolves around concurrency. The idea of parallel programming, where several computations are executed at the same time and potentially interacting with each other. Even these challenges, not everything looks dark towards quantum computers. There have been already some significant achievements. For example, Peter Shor from AT&T Laboratories, whom developed an algorithm to factorize large numbers. With conventional computers and algorithms, it is a problem that takes years to solve and is so complicated that settles the principles of RSA encryption. With quantum computers and this algorithm, this problem is solved in a matter of seconds. This is an example of the exponentially hard problems we face and the power quantum computers will have to solve them. Also, a company has already developed the first quantum computer with a 128-qubit processor sold at the price of $10 million. Even great accomplishments have been already made, and future is aiming towards quantum computers, with important organizations doing research on this, like Google and IBM. It will take a long time before we can have a personal commercial quantum computer. But as large superquantum computers are developed, so will developments will be in technology and computer science. There are many expectations and theories of how the future will look like once we achieve more of this technology. Some seem a futuristic world where machines are programmed for well-being 24/7, self-driving cars, wireless telepathic communication, and much more can be found in articles that make them look like science fiction books. Truth is that the power of quantum computer aims towards most of these concepts, such as quantum simulation, artificial intelligence, face and voice recognition, information processing, and true randomness. However the future awaits for us, truth is that it will not look like something we already know.